Hi everyone, welcome to the General Maths 3-4 lecture for the September lecture series. My name is Manjot and I will be taking you through the lecture today. Just before we begin, I'd just like to introduce everyone to HR Notes. So HR Notes has been providing heaps of resources to students across Australia since 2007 so that you can all thrive in your studies. We've also been offering these particular lectures since 2015 because they're in line with our mission to help students as much as possible. And we also provide a lot of resources to further help students, such as the study notes, the lectures like the one that you're watching today, the online discussions, engaging online revision videos, newsletters, ATAR calculators, and other articles, and heaps more. So if you would like more information, please check out the info doc under the resources tab. Or if you have any questions about these resources, please pop them through into the Q&A chat. Okay, let's get started with the lecture. We have a lot to go through today. So like I said, my name is Manjot, and I will be taking this lecture today. So just to briefly introduce myself. So I graduated recently with an ATAR of 99.80 and a 50 study score in further maths. And I'm currently studying a Bachelor of Biomedical Science at Monash. And the subjects that I did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths. Okay, so let me know if you have any questions. Otherwise, we'll get started with today's content. So we'll basically be revising data analysis, recursion, and financial modeling, which is probably what you would have covered in terms 1 and 2 of this year. So we're just going to be going through this, revising all the concepts so that you're ready for your end of year exam. So we won't have time to go through matrices or networks, but you would have gone through that fairly recently. So you should be quite familiar with those topics. So the structure of this Q&A, this lecture today, is that there will be no designated breaks, and that we will be using the Q&A software. So if you have any questions, please pop them through into there. I'll be monitoring the chat throughout the duration of the presentation. So if there are any questions, just pop them through and I'll be answering them as they come up. Okay, so first of all, we'll be looking at the different types of variables that are used in data. So first and foremost, we have categorical and numerical variables. So these are the two different branches of data. So categorical variables are usually representing some form of category, whereas numerical variables usually represent values, measurements, or any quantities. So furthermore, for categorical variables, we have nominal and ordinal categorical variables, where the nominal variables have no particular order, whereas the ordinal variables usually have an associated order. And for numerical, we can usually have discrete and continuous numerical variables, with discrete numerical variables being variables that we usually count, and continuous numerical variables usually being those that we measure. So just to go into a little bit more detail about categorical variables. So categorical variables usually represents data that is divided into discrete categories. So that could include stuff like eye color, football team, usually qualitative data. So data that we usually describe as opposed to quantify. And furthermore, for categorical data, we can have nominal or ordinal categorical data. So for nominal categorical data, that just represents sort of basic categories that usually have no associated order to them. So for example, hair color. We can have blonde, black, brown, but these colors don't really have an associated order. So if someone has a blonde, it doesn't mean they're, their hair color is, above a different hair color. So it's just basic categories which have no associated order. This is in contrast to ordinal variables, which usually have a natural order. So just in the way in which we naturally arrange ordinal variables, they will have an associated order. So for example, An ordinal variable could be someone's BMI index. So for example, it could be underweight, average, overweight, morbidly obese. Another example could be, for example, your age group. For example, it could be infant, toddler. It could be, a primary school student, a secondary school student, an adult, a senior citizen. So those things just have a natural order to them. Okay, looking at a bit more detail, looking at numerical data variables in a little bit more detail, it's usually representing quantities that we usually count. For example, it could be the height or the number of students. So it's an associated quantity. And furthermore, we can have discrete or continuous variables. So discrete variables are usually those that you count. So that is a question that I like to think whenever I'm classifying numerical data. Is this a variable that I'm going to count, or is it a variable that I'm going to measure? If it is something that I'm going to count, then that would be a discrete numerical variable. So for example, the number of people attending this lecture could be a discrete numerical variable. Because, I could count all of you. I wouldn't measure how many students there are. I would count. And we would get an accurate value. So for numerical continuous variables, however, it's usually sort of variables that you usually count. Measure. So for example, the height of all the students attending this lecture would be a continuous numerical variable because I would have to measure the height. I can't count the height. And usually discrete numerical variables have a finite number. So whereas numerical continuous variables have infinite possibilities because your height could be, 2 meters exactly, or it could be 2.000001 meters, for example. So that's just the difference between numerical continuous and numerical discrete variables. Okay, now looking at just a quick practice question, a question that you're more than likely to get on your exam 1. A question that asks about 2 variables and you have to classify them. So we have the variables age, under 55 years and over. Or we have, and we also have preferred travel destination. So if we just look at age quickly, although age you would normally associate with it being a numerical variable because this is usually something that we can measure or count, in this case, the brackets give us a little bit more description of how the age is being classified. So age is actually being classified as under 55 years and over. So these are actually discrete categories in which individuals will be placed into. So therefore, this will actually be a categorical variable. Now, if we look at it in terms of it being nominal or ordinal, so being under 55 years or younger, and then being 55 years or over, that is actually an associated order, just a natural order. If you're under 55, you're going to be younger, as opposed to someone who's 55 years and over. So therefore, there's a particular natural order, so therefore it would be an ordinal variable. Now, if we come to the preferred travel destination, there are obviously no quantities involved. So straight away, we can say that it's going to be a categorical variable. And if we look at the categories that we've been given, so domestic and international, these two sort of categories don't really have a natural order. So we can't really arrange them in a way such that we have placed them in a ordinal manner. So therefore, this would actually be nominal. So now the question asks, are they both categorical variables? And the answer here would be yes. But are they both numerical variables? No. A numerical variable and a categorical variable respectively? No. D's also no, because we have 2 categorical variables. So straight away, we can just say that it's going to be A as our answer. But just checking the rest of the answers just to make sure. Okay. Let me know if you have any questions in the Q&A. Okay, so now we'll be moving on to the types of data. So we can have either univariate data, and as the name suggests, we're only looking at one variable in this case. So that variable, so uni literally just means one variable. So when looking at univariate data, we're only describing or measuring one variable. So only one variable or one quantity or one sort of value or one sort of category is being manipulated, depending on what type of variable it is. So for example, color is something that we might be recording. So for example, the color of, cars that, pass through a particular intersection. We're only looking at one variable here. So therefore, this would be univariate data. However, for bivariate data, we're actually looking at two variables. So in this case, in the example given, we are looking at year 7s, year 8s, year 9s, and year 10s, and we're looking at their mode of travel to school. So here we are manipulating two variables. First of all, we can manipulate the age group or the year level, and we can also manipulate their mode of travel. So there's two variables that we have to account for. Okay, and in terms of univariate data, there are multiple ways that we can actually depict this in a graphical or tabulated manner. So this is really important because if we just get a big block of just random numbers or random frequencies of certain, we are going to get really confused on how to analyze that data. So usually what statisticians will do is graph that data such as to make it more receptive to whatever the audience is, and just to overall increase how easy to read and interpret that data is. So if you have a categorical variable, the way that we can depict it is is using frequency tables, percentage frequency tables, or bar charts. Whereas if we have a numerical variable, the ways that we can depict this, again, using frequency tables, but this time they will look a little bit different. We can also use dot plots, box plots, stem and leaf plots, and histograms. So now we'll be just quickly going through all the different types of graphs and how we can sort of interpret and also graph them. Okay, so first we have frequency and percentage frequency tables. So as their name suggests, we're just denoting the frequency of the particular variables. So for example, if we're looking at the preferred social media platform, we can denote the frequency. So let's just say we have a sample of 83 students and we're denoting their preferred social media platform. A frequency table would literally just list down how many students have a preferred social media platform. So the frequency just represents the exact number of people in that sample that prefer that social media. And then we can actually convert this into a frequency, which makes the data even more sort of easy to interpret. So the total percentage frequency is obviously going to be 100% because that represents the entire data set. And then the percentage is just a percentage of how many people in that 100% will have that preferred social media platform. So this is really good for depicting data, as we can immediately see that Facebook has a really high frequency. So in this case, even for just a normal frequency table, we can easily tell that Facebook has a really high frequency. But let's just say we had 20 or 30 variables instead. So let's say we had 20 or 30 different social media platforms. Just using frequencies might be a little bit hard to sort of see the actual relationship between, or to determine what's the modal frequency or what's the median, which will come through next. But if we're just trying to immediately determine what social media platform has the most highest preference in the data set, we might use a percentage, because we can easily see out of these that Facebook is the highest. But both of them will have different uses depending on your type of data. Okay, now we have bar charts. So bar charts are literally just another way of representing frequency, but this is more of a graphical way of representing it as opposed to a more tabulated way. So bar charts have the variable that you're measuring. So for example, your categories on the x-axis, and they will have the frequency on the y-axis. So when you're drawing a bar chart, some important rules are to label all the axes and also rule any lines properly. The bars also need to be of equal width with space between them. So we'll be looking at a different type of graph, which is called a histogram, which sort of looks like a histogram, but there are no spaces. So really important to have spaces in between. So if we just quickly look at this particular bar graph that we have here, it denotes the number of pets that people have at home. So for example, we can easily tell from this graph that dogs is the mode here, or the highest frequency. So most people have dogs in our sample. And if we were to quickly estimate how much people that was, we can approximately say around 138 or 139. So bar graphs are really good for easily or visually depicting frequencies of data. Okay, so now we're going to quickly look at how we might describe categorical data. So describing data is really important and also part of the study design dot point. So these sort of describe or explain paragraphs pop up really often on the exam. So you should be really familiar with how to describe data, what you need to describe in terms of when you're describing data, and also how to describe it. So what you need to do. So I would personally recommend having a sort of structure already pre-prepared in your data book, your summary book, and just having that with you in the exam. And just leaving like blanks for certain values. So, but just generally the overall structure is first of all summarizing the context. So if the data is about the number of people pets have at home, or the number of categories. Yeah. So all maybe the year level of students, or it could be what we looked at before, the preferred social media platform. You have to summarize what the context means, how the data, what the data represents essentially, and also how many people were in the sample. So really important to summarize the context first. And then the next step is to identify the mode or the modal category. So basically, which category had the highest frequency. So for example, in the previous slide, we looked at the frequency of pets at home, and we could tell that the modal frequency the modal category was dogs. So then we would have to probably say that dogs were the modal category, and also probably quote the frequency as well. So 138 people have dogs at home, etc. Then you need to quote any other frequencies of interest. So there could be, any outliers potentially, or frequencies with extremely low frequency. So stuff like that you might need to quote as well. But usually these first three steps are what we're usually doing. Okay, here is a typical question that you might get. So comment on the data from 23 countries shown in the frequency table below. Okay, so first step is describing the data, or just summarizing the context. So the climate types of 23 countries were classified as being cold, mild, or hot, and the majority of the countries, 60.9%, were found to have a mild climate. So here we have summarized the context. Then we have quoted the modal frequency, which was the mild climate with a 60.9% frequency. And we might also quote the hot and cold frequencies. And when we're quoting frequencies, we always quote the percentage frequencies. We never just quote the raw frequency. So 6, 14, or 3, we will never quote those. We'll always quote the percentage frequencies. Okay, so so now we've looked at all the categorical variables. So now we'll move over to numerical variables. So numerical variables can also be represented in the form of frequency tables, but in this case, the data is usually grouped, as you will see soon. So because we can have multiple sort of, so for example, categories, we can usually have a discrete or a small number of categories. Whereas for numerical variables, you usually have a lot of. So for example, if you're recording the age of, everyone in a particular room, for example, it could range from anywhere from between, 10 to, 100. So we won't want, 100 categories and reporting the frequency, because we might only have one person who's 26 years old, for example. So it's really pointless to record the frequencies of each age. So therefore, what we might do is we might group the data. So as opposed to recording how many people are aged, particularly 26, we might just record everyone, or we might group the data from 0 to 20 years old, 20 to 40 years old, and 40 to 60 years old. And then record the frequency there. This way, the data is a lot more useful, and it enables us to record the patterns in the data a lot more easily, as opposed to recording the individual ages. That way, the data doesn't really mean anything. This way, we can immediately see that the most frequent age group is those aged 20 to 40 years old. So they're really important to notice the difference between frequency tables in numerical and categorical data. So numerical data can also be represented in the form of dot plots, but this is usually for discrete numerical data. So basically what we do when we're plotting a dot plot is, instead of having a frequency percentage table, we usually have some form of a dot plot. So the dot plot literally just does is we have a particular number and we just record its frequency. This will usually be a really good measure of data when we have a really small sort of number. So for example, it could be probably not the age of students in a room, but maybe stuff like, if it's like, for example, the month of birth. Actually, that's more sort of categorical, but it could be stuff like the number of cars that cross the road. So, what are the different numbers of for a particular color. So it's very similar to categorical variables, but we also use it for numerical variables as well. And again, the number of dots will usually represent the frequency. What these will be really good for is actually estimating the median. So median, we will come back to that a bit later on, but it's just going to be the middle point of the data. So if the data was laid out in an ordered manner, what would be the middle value? So we'll come back to that in a second. Okay, so then we have stem and leaf plots. So stem and leaf plots are basically a type of plot which has two components. So it has a stem and a leaf. And what the stem represents is the first digit of a data, or if it's, for example, a decimal, it could represent the decimal part as well. So we'll look at that in an example. And the leaf represents the last digit. So this way, if we have, for example, age of the people in a room, it's a much more easier way. So instead of having, 1, 2, 3, 4, we can have 1, 2, 3, 4, or the tens digits on the stem, and the leaf could be the ones digits. So for example, if you're 12 years old, the 1 would be the stem and the 2 would be the leaf. So look at that in an example. So here is an example of what a stem and leaf plot might look like. So for example, if we're recording the number of people who are a certain age in a particular room, the stem could be, 10s, 20s, 30s, 40s, 50s, and 60s. And the leaf represents the actual numerical digit. So in this case, again, we're sort of recording all the individual entries. We're not grouping anything. But this way, it's more powerful because if we have, for example, a lot of people in their 20s, there would be a lot more data entries. And therefore, we can see immediately that there are more people in their 20s as opposed to 50s, for example. So the legend is the most important part of the stem and leaf plot. So the legend or the key usually represents what the data actually means. So for example, in this case, 1/0 is equal to 10. But what it could also be is, for example, if we have, just give me a second. So if we have, for example, 1/2, it could also be 1.2. So it doesn't always have to be, tens. Really important to look at the key in terms of what the data actually represents. Okay, so next we have histograms. So like I said, they look very similar to a bar chart, but there is no space between the columns. And we don't have space between the columns because we're usually, again, grouping the data. And I'll show that, and I'll show everyone what that means in a second. But what we have on the x-axis is the variable, and again, we will have frequency on the y-axis. So histograms are really important to represent the shape of the data. It can also be used to represent the center, any outliers, and spread. So overall, histograms are just a really good way of representing how the data is distributed, which is what we're mainly concerned with when doing data analysis. So what we have done here, so for example, we have grouped the data. So in terms of football game attendance, so if you've attended 0 to 4 games, 0 to 4 games, you're in the same sort of category almost. So 5 to 9 games, you're in the same category. 10 to 14 games, you're in the same category. So this way we can really see how the data is distributed. So most people have attended 0 to 4 games. And from this, we can also estimate the shape, the spread, the center, and the outliers. Okay, so another type of graph that you're going to see, and we're going to come back to this when we talk about data transformation, is the log histogram. So the log scale, so if you're not familiar with the log scales, it's usually to simplify really large values. So for example, if we have, let's just say, so first of all, I'll quickly explain what log really means. So log is, so for example, if we have 2, actually, let me change that up. Let's just say if we have 10 to the power of 2, which equals to 100, we can actually transform this and write it as a log. So basically we have a base, and we also have, a solution, and we also have the power. So the log equivalent of this equation would essentially just be log the base, which was 10, of 100. And that would actually be equal to the power 2. So this way, instead of representing 100, we might just write the answer as 2 and show that it is actually a log scale. And this is really useful when we have a really broad range of data. For example, let's just say you have a particular data set where you have values in their tens, but also in their millions as well. We would require an extremely large scale to represent that data. And also another problem that we would encounter is the data might not be useful, because let's say we have data concentrated in the tens, and then we have data concentrated in the millions. So we can't really establish any relation. It might just look like two separate graphs, honestly. So in this case, it's really important to use a log scale to estimate how the data is being distributed, because instead of having 10, then hundreds and thousands, we might have 1, 2, 3, and it would represent increasing powers of 10. So what the data would really look like is, instead of having 10 and then 100 and then 1,000, which is not a balanced scale, we might have 1, 2, 3, 4. And we'll show that using an example. So here is just an example of where we might use. So for a normal scale, we'll have 0, 10, 20, 30, 40. However, in a log scale, there will be constant multiplication by 10. So we might do 1, 10, 100, 1,000, 10,000. But it's really hard, but we have the same sort of gap, which would be very inaccurate, right? So this, from 1 to 10, is the same as 10 to 100, which is just not inaccurate. So instead what we'll do is we'll use log scale. So this might be 0, this might be 1, and this might be 10, for example. So we're using log scales in this case. And by using those log scales, we have made the data so much more accurate, or the way that we've represented the data. So just some properties of logs. So log, if a number is greater than 1, its log is going to be greater than 0. Another property of log is that if a number is greater than 0, but less than 1, its log is negative. And if a number is 0, its log is undefined. So log is always going to be the number inside the log. So log of 10. So when we're saying log of 20, we're usually representing the number inside. So if it's, for example, 20, it's greater than 0, this number, what this is equal to, it's going to be greater than 1. However, if it's less than 0, if it's more than 0 but still less than 1, for example, half, this value will actually be less than 1, so it will actually be a negative value. And if it is, and if this value is negative inside the log, the log will be undefined. So we can't have log of negative numbers. So when displaying logs on the scale, we use their order of magnitude. So for example, if it's 0, 10, 100, 1,000, we will use 0. Not 0. No, it doesn't start with 0. Yeah, it will start with probably 1, 2, 3, 4. Instead of having 10,000, 100, 10,000, 10,000, 100,000, million. So here's an example of what it might look like. So we have a log scale here. So this would be, instead of being 0 to 1, it would instead be from 0 to 10. And then this one, instead of being from 1 to 2, it's actually 1 to 100. And then this one, instead of being 2 to 3, it will instead be 100 to 1,000. So instead, just the pattern here is 3 just represents 10 to the power of 3. 4 represents 10 to the power of 4. 5 represents 10 to the power of 5, and so on and so forth. So this will be 10,000. So that's the actual value. We've just used 1, 2, 3, 4, 5 to simplify this. 100,000, so that we can have them all on the same scale. So this is essentially what we're looking at. So when we get questions, it's really important to not write it's between 0. So if the question asks how many people have, whatever this represents, between 100 and 1,000, it's not going to be all of these, because 5, so a lot of people might think, if it's 1 to 5 and people are only between 1 to 5, no one is between 100 and 1,000, or none of the data values lie between 100 and 1,000. That is not true. These actually represent log scale. So this 2 to 3 represents 100 to 1,000, and so on and so forth. Okay, so this is a handy log guide, but obviously you will have your calculators, so it will be pretty straightforward. Okay, so now we'll be looking at descriptive statistics. So descriptive statistics is basically when we're just a set of values used to represent numerical data. So the values that we usually have to calculate when we have a numerical data set is the minimum value, the interquartile range, the median value, the upper quartile, and the maximum value, and sometimes also the IQR and the range. But these values, so these values are really important when and whenever a question asks to give the descriptive statistics, this is what it's referring to. All of these can be done on the CAS. So you shouldn't even be spending time doing it by hand, just a waste of time on the end of your exam. So all should be done in your exam. Usually it's under the univariate data analysis menu, which you all should be familiar with. So what can we do with the 5-number summary? Well, from the 5-number summary, we can calculate a whole bunch of other statistics. So we can calculate the IQR, we can calculate the range, we can do outlier calculations. It's extremely common questions on the exam 2 specifically, which we'll come back to in a second. So IQR literally just represents the interquartile range. So it's just found by doing Q3 minus Q1. And what it's essentially doing, it's finding the middle 50% of the data. So where does the middle 50% of the data lie? Between what values? So Q3 represents the upper quartile and the Q1 represents the bottom quartile or the lower quartile. And then therefore this would just, the IQR would just represent the middle 50% of the data values. And then from this, we can work out the lower fence value. So the lower fence value tells you, so we'll look at a dot plot, but it will tell you where the outliers lie. So for example, if we have, data between 2 and 100, for example, so the maximum value is 100 and 2 is the minimum value, but we don't know if these are outliers. So we might use, or just any values in the outlier, we can use something called a lower fence and an upper fence. So all of these formulas are given in your formula sheet. But when you use these formulas, so Q1 minus 1.5 times IQR and Q3 plus 1.5 times IQR, you can easily determine the outliers because it will give you a value. So let's just say the lower fence, we do this calculation and we get 5. So therefore, any values that are below 5 are actually going to be outliers. Similarly, let's just say we had an upper quartile value of 70. So any values above 70 are going to be outliers as well. So therefore, this is the range over here. So between 5 and 70, you're not an outlier. Below or above those values, you're an outlier. So a really important question because on the exam, you're going to get questions asking you to verify that something is an outlier, or you will have to use the lower or upper fence calculations. Okay, so in terms of box plots, they are a visual display of the 5-number summary, which is what we calculated. So the mean, the minimum, the Q1, the median, the Q3, and the maximum value. So the box plot is a really good display of this data because it allows us to represent, so first of all, it makes the values really clear. So we can easily determine if something is an outlier from looking at a box plot, if something is, what's the median, what's the upper quartile, what's the lower quartile. But also, it's a really good display of the shape of the data. And we'll have a look at the shape of the data in a sec on the next slide. But this is really important because if we just want to, quickly see what the data is it negatively, positively skewed, or how the shape of the data is, as well as just quickly estimating the 5-number summary. So a really good display of the 5-number summary here. Okay, so now we'll look at the shape of the data. So the shape of the data really gives us information on how the distribution actually looks, or how the values are actually distributed in real life. So the shape that we can have are positively skewed, negatively skewed, approximately symmetrical, or bimodal, where bimodal is actually going to be really rare. So you'll only be mostly assessed on these first 3 shapes. So what positively skewed literally means is we have most of the data skewed. So skewed just means literally where the data is sort of ending. So if we look at this, let me redraw that. If we look at the positively skewed data, we have most of the data concentrated on the left-hand side and only a little bit of data concentrated on the negative on the right-hand side. So what that means is this is essentially a skew. So you have a skew on the positive side of the data. So this is the positive side and this is the negative side. And the data is skewed towards the positive side, where we have most of the data concentrated on the left-hand side and being skewed on the right-hand side. So that's why this is termed positively skewed. Negatively skewed will just be the opposite. Most of the data would be concentrated on the right-hand side, and we'll only have a little bit of data on the left-hand side. So that would also be negatively skewed. Approximately symmetrical, we would have no skews of data, or if an alternative way of saying it is, we have skews on both ends, technically. So basically, this is approximately symmetrical because most of the data is concentrated in the center. And the data sort of looks symmetrical. So if you were to put like a mirror here, the data would approximately, look equal on both sides. So that's why it's termed approximately symmetrical. And if we have bimodal data, we have sort of approximately like 2 planes of symmetry. So basically the data from this side will sort of be symmetrical, but essentially what we have is 2 modes. So in an approximately symmetrical data, positively skewed data, and negatively skewed data, we will have 1 mode, which will either be on the left-hand side, on the right-hand side, or in the middle. In a bimodal data distribution, we'll have 2 modes, probably on the left and also on the right-hand side. They could also be in the middle-ish, but fairly separated apart. So you can clearly tell when something is bimodal. So here is how that might look in terms of a box plot. So in terms of a box plot for a positively skewed data, the actual distance between the sort of like the right-hand side of the box will be much greater than the left-hand side. And for the negatively skewed data, it will be much greater on the left-hand side. And for approximately symmetrical, the boxes should approximately be even in size. Okay, so that's essentially how we determine outliers, the center, the spread, and the shape of the data. So we'll come back to a few more measures of center, but this is essentially the different ways that we can represent univariate data. Okay, so now we'll quickly look at the normal distribution. So the normal distribution is essentially when we have data that sort of is symmetrical, and it follows a certain distribution. So the distribution is called a normal distribution because most things in nature will have this type of distribution. And the distribution is approximately symmetrical, whereby 50% of the data will lie on the left-hand side of the median, and 50% of the data will lie on the right-hand side of the median, which is usually the case, but the median will now be splat bang in the center. So this is the median here. So another descriptive statistic that we don't really look at in much detail is called the median. So the standard deviation. So if we look at if we quickly recap the measure center, which you all should be really familiar with, we have the mean, median, and mode. In a normal distribution, the median is actually equal to the mode, which is then equal to the mode, which is then equal to the mean. And if we look at the standard deviation, so standard deviation is essentially just a measure of the spread of the data. So how spread out the data is. Something that might be more spread out will have a greater standard deviation, whereas something that has a lower standard, sort of spread of data will have a lower standard deviation. So the normal distribution looks at the relationship between the median and the standard deviation to estimate how much data actually lies between two certain values. So when that might be useful is, let's just say we're doing a study on the let's just say the distribution of orange sizes or orange diameters in a population. So we're not going to look at every single orange in the entire world, but what we might do is look at a sample of orange from just one particular field, or it might just be from one particular tree. So what we might do is, from the distribution of the diameters from that particular orange sample, when we draw the normal distribution out, or we plot that data out in using a histogram, we will see that the data is approximately symmetrical. And what we'll see in nature is something called the 68, 95, 99.7% rule. I'll come back to that slide just quickly, but what we will see is approximately 68% of the data value. So let's say in the sample, we had 100 oranges, 68 of those, so 68%, 68 of those will lie one standard deviation of the mean. So what that essentially means is whatever one standard deviation is, so let's say the mean is, 2 centimeters and the standard deviation is 1 centimeter. So we are expected to see that the majority of or one standard deviation, actually that's not a good example. Let's just say the mean diameter of the oranges that we were looking at is 5 centimeters. And the standard deviation or how spread out the data is 1 centimeter. So 6 plus 1, which is 7, 6 centimeters, and 5 minus 1, which is 4 centimeters. So what this tells you is that approximately 68% of the data, or 68 of those oranges, will have a diameter between 4 and 6 centimeters. Whereas 95% of those oranges will be between 2 standard deviations. So what is 2 standard deviations? So 3 centimeters and 7 centimeters. So approximately 95%, which is like the majority of the oranges, will be between 3 and 7 centimeters. And around 99.7%. So that is about all the sample, or about 99.7 of the oranges, which is approximately just 100. So most of them will lie within 3 standard deviations. So they will have approximately a diameter between 2 and 8. So 99.7% of the data values will be between 2 and 8 centimeters. 95% of them will be between 3 and 7 centimeters. 68% of them will be between 4 and 5 centimeters. So that's essentially what the normal distribution is. So if we were to, go, so let's say I was in an orange juice production company, I would, want the statistics of how many oranges I would approximately expect to get. I would need to buy to produce this much amount of juice, for example. This is where it might be really helpful. Okay, so again, I'm just going to quickly go through the standard deviation. So the standard deviation describes how the data is spread around the mean. How spread out the data is. Is it like a little bit spread? So for example, something that might be a little bit spread out is, what is a good example? So it might be stuff like your oranges. Oranges are usually roughly the same amount of size. But something that might be a little bit more spread out is, for example, your study scores. They might have a greater standard deviation because we have values ranging from 0 to 50, for example. So if the mean is 5 and the standard deviation is 2, one standard deviation would mean, above the mean would mean 7. Whereas one standard deviation below the mean would mean 3. So 5 minus 2 or 5 plus 2. So now that we know what the standard deviation is, and what the mean is, and also what the normal distribution is, we can now use something called a z-score. So what the z-score does is it standardizes the distribution. So let's just say you were, again, looking at apples now. So let's say opposed to oranges, you're looking at apples now, and the diameter of apples in a sample. So let's just say we want to compare that to the diameter of oranges. So let's say we pick up an apple and an orange. We want to compare how the sizes of those apple and oranges compare to the actual population. Is my apple bigger or is my orange bigger in terms of how apples normally are and in terms of how big oranges usually are? So that is when we might use the z-score. What the z-score does is it standardizes the value to a standard normal distribution. So you will get a value ranging from -3 to +3. And that will tell you how many standard deviations above or below your value is. If you get a negative value for your z-score, that means that the distribution is that many standard deviations. So let's just say you get -2.7. That would mean that the value or the size of the apple or the orange is 2.7 standard deviations below the mean. Similarly, if you get a value of, let's say, +1.2, that would mean that your apple is 1.2 standard deviations above the mean of normal apple sizes. Okay, so here's just a quick example. If you are watching this lecture, I would encourage you to pause now and have a go. Otherwise, I will go through the solutions now. So the heights of females in a small country town are normally distributed, with 16% of the females being more than 160 centimeters tall, 2.5% of the females being less than 115 centimeters tall, and the mean of the standard deviation is what we're trying to determine here. So we know that 16% of the females are above 160 centimeters tall. So what do we know about the normal distribution? So if we just look at the normal distribution graph quickly, we know that 68% of the data will be within one standard deviation of the mean. So how much data must lie above the standard deviation of the mean? So if 68% of it is between 2 standard deviations, the total should always equal to 100%. So therefore, if 68% is just this much over here, what is the rest of it? So the rest of it is going to be, 32%. So therefore, we will have 16% on the left-hand side, because remember, it's approximately symmetrical. So it's symmetrical graph. So 60% here and 16% here, in total, equaling to 100%. So now that we have determined how much is 16%, what does this graph say? So it says that 16% of it are more than 160 centimeters tall. So in this case, what we can actually use is Okay, so now that we've determined we have 60%, so we know that 160 centimeters should be here. So it's one standard deviation above the mean. Well, we don't know what the mean is yet. Okay, now let's look at 150 centimeters. So what they are saying is 2.5% of the females are less than 150 centimeters tall. So if we go back to the graph, so they're saying 2.5% are less than 150 centimeters tall. So where is the bottom 2.5% of the data? It actually is here. So it's between, so it's less than 2 standard deviations less than the mean, because between 2 standard deviations is 95%, and we have 5% left over on either side. So 2.5% on one side, 2.5% on the other side. So therefore 2.5% of the data is going to be over here. So therefore this must be 115. So now there's two ways. So you can either use the z-scores to actually do this question a little bit more easier, or alternatively, we can just work out what we need to add consistently to get to 160. So we have 1, 2, 3 values. So therefore, what we're essentially doing is 160, so the distance between 160 and 115 divided by 3. And that way we will get what this interval represents. So if we do that, we will get 160 minus 115, we will get 45. So 45 divided by 3 is equal to 15. So this distance from one interval to this interval represents 15. So 115 plus 15, 130. 130 plus 15, 145. 145 plus 15, 160. So therefore, the mean is actually going to be 145. And the standard deviation is actually going to be 15 centimeters. So just by knowing how to draw your how to draw your normal distribution, and where the data values sort of lie is what's required for this question. So therefore, the answer here will be C. It's a little bit of a tricky question. So if you use z-scores, it's going to be a little bit more difficult, but I would personally recommend just drawing out the normal distribution. So here is just a quick summary of univariate data analysis. So we have 4 different types of variables. We can have categorical or numerical variables, and furthermore we can have nominal, categorical, or numerical, nominal and ordinal categorical variables, and discrete or continuous numerical variables. And in terms of data, we can either have univariate or bivariate data. So bivariate we'll come back to in the next block. So in terms of the representation of data, we can have multiple ways that we can represent the data, and that will depend on the type of data and the type of variable that we actually have. And then in terms of analyzing the data, we will analyze the data using descriptive statistics or the 5-number summary. We can also describe the shape, the center, and the spread of the data. And then in terms of normal distribution, we really need to understand the 68, 95, 99.7% rule and use that to estimate probabilities or the number of people that might have a particular, or the number of data values that might be in a particular above a or below a standard deviation. And we also need to know how to standardize data in using z-scores. Okay, so now we'll hop on to bivariate data. So bivariate, again, meaning 2 variables. So 2 variables that we are changing or manipulating. So univariate data is really good at telling us what. So in terms of, let's just say, the number of cars in a parking lot. The number of students in a particular classroom. The number of people that have brown hair. The number of people that have black hair. It's really good at saying us what it is. But if we want to actually compare data, we want to compare how someone's height might be associated with their weight. Bivariate data is what is the go-to here. So bivariate data is the comparison of data and looking at the associations of data between 2 different variables. And from there, we can establish correlation or causation. So really good in terms of comparing and establishing a sense of causality. So what is the relationship between age and height? does gender play a role in someone's favorite color? How do the average temperatures in all major Australian cities compare? So bivariate data is, a really good way of determining the relationship between two particular variables. Okay, so when we are looking at bivariate data, we will have two different types of variables. So like I said, bivariate data, looking at two or more variables. So we will have explanatory and response variables. So explanatory variables are usually, in other terms, called the independent variable. So it's the variable that we're usually manipulating. And the response variable is usually, whatever's going to change as a result of that explanatory variable. So for example, an explanatory variable might be your height. And as a result of that, it might influence your weight or vice versa. But usually it's going to be height influencing your weight. So usually there will be a sense of a directionality. So you will know what the explanatory and response variable is. Or if that is something you're trying to investigate, you need to have an explanatory and response variable already established. Okay, so explanatory variable, also known as the IV or the EV, is the variable that you're going to change whenever you're doing a study. So it's usually represented on the x-axis of any type of data that you might use to represent this data. And the response variable is what's going to be affected by changing the explanatory variable. So for example here, age will be affected by shoe size. So therefore age is the explanatory variable and shoe size is the response variable. Okay, so in terms of the representation of data, there are again multiple ways that we can represent bivariate data, depending on what type of variables we have. So if we have two categorical variables, we can represent it using a segmented bar chart or a two-way frequency table. If we have the explanatory variable being numerical and the response variable being categorical, we can use parallel box plots. If we have a numerical explanatory variable, but more than two categorical variables, we can use a back-to-back stem and leaf plot. And if we have two numerical variables, we can just use scatter plots. Okay, so let's just quickly look at how these graphs actually look like and how we can interpret them. So in terms of percentage frequencies, percentage segmented bar charts, they usually have the explanatory variable on the x-axis, and the frequency again will be on the y-axis, but this time the data will usually be split. So for example, if we're looking at cold, mild, and hot temperature levels on the days, in the number of days in 2010, 2011, and 2012, it's actually being split here. So although we're recording frequencies, the frequencies have been split in every year. So, this way we can easily tell, 28% or, 25% of the, 30% of the data or 30% of the days in 2010 were hot. So here we have two variables, so not only the number of days at temperature levels, we also have the type of temperature. Okay, next we have two-way frequency tables. So again, very similar to percentage frequency segmented charts. We have, again, two variables. So one variable, usually explanatory variable, is going to be on the left-hand side, and then the response variable on the top. So these numbers or the percentages in the middle usually represent the frequency or the percentage frequency of, let's just say if we're looking at 36%, it represents the frequency of people that are for a particular issue in year 11. And 64% of them are against the issue in year 11, and so on and so forth. So again, two variables here, attitude and year level. Next, we have back-to-back stem and leaf plots. So in this case, we again have two variables. We have not only the eye color, we also have the frequency, or how many people have that eye color. So in this case, we have another stem and leaf plot. So here we have the stem, 5, 6, 7, 8, 9, 10. And then we have the leaf, which represents the actual values. Next, we have parallel box plots. So parallel box plots have one categorical variable and one numerical variable. So they are really good for comparing the distribution of two different variables. So let's just say we're trying to compare the number of hours spent by students at a particular, in a particular subject doing their homework over the weekend, or not over the weekend, over the week for a particular subject. We're going to look at boys and girls separately, and then we can compare. So on average, girls spend more time doing their homework over the week as opposed to boys. So this is what parallel box plots are really good for. So when you're asked to compare data distributions, you're again going to be asked to, so in this case, what you're actually asked to compare is actually a little bit different. So you are actually going to be asked to look at the center, spread, and shape of the data. So when you're looking at the center, you're going to be looking at stuff like the median, the mean, and the mode. When you're looking at the spread, you might look at the IQR or the range of the data. When you're looking at the shape, you might look at whether it's positively skewed, negatively skewed, approximately symmetrical, does it have outliers, does it not have outliers, so on and so forth. So those are things that you're describing when you're describing bivariate data. Okay, so here is a sample, sort of sample response when we're comparing box plots. So first, we have described the distributions. So how do the distributions, the shape of the distributions vary? So for boys, we have said that they are negatively skewed, or the distribution is negatively skewed. Whereas for the girls, it is positively skewed. So just basically, you're just describing the shapes and comparing them. Then you need to talk about the outliers. Even if there are no outliers, you still need to mention that there are no outliers. A lot of people forget this when there are no outliers. They just don't mention it at all. Okay, another thing that I want to quickly talk about is when to use which descriptive statistic to talk about the data. So most of the time, I would just say the rule is to use the median and the IQR when you're comparing distributions. Technically, you can use the mean, but the mean is only helpful when the distribution is approximately symmetrical. So if there is some type of skew in the data, it's not going to be a good measure of center. So in that case, we need to use the median. So I would usually just stick to median regardless. So here we have compared the medians. We have said the median score for the boys, m equals 23, is higher than that for girls. And then lastly, we need to compare the spread. So when we're comparing the spread, we can talk about the IQR. Again, we can either talk about the IQR or the range or the standard deviation. Again, standard deviation and range are non-resistant statistics. So they're actually impacted by any outliers and also any skewed data. So therefore, IQR is again a really good measure because it's only measuring the middle 50% of the data. So here again, we've compared the IQR. So this IQR is smaller for boys, IQR equals 10, than for girls. So here I've also compared the range as well, but that's honestly a little bit of extra. But comparing the shape, outliers, median, and IQR is essentially what you need to get full marks. Okay, so next we'll look at scatter plots. So scatter plots are again just a type of graph which represents two numerical variables. So we will have the explanatory variable on the x-axis and the response variable on the y-axis. And what these dots represent is sort of like the union between the explanatory and the response variable. So if we were to interpret a particular data point, let's just say this one, well, how we will interpret is we would look down and see what the x variable is. So, we have a explanatory variable value of around 10. And then we can look at the y variable. So that would be approximately 20 or 21. Yeah, probably 20. So if we were to write the x and y table, the x would be 10 and the y would be 20. So that's how the scatter plot is really useful, because it represents, it's usually just like dots, but it's really good for representing the shape or the strength of association between two particular variables. So when describing scatter plots, and these questions come really often on the exam, especially when they've drawn a scatter plot for you, you need to be looking at the strength, direction, and form of the scatter plot, and they will tell you what they want you to describe. So when you're describing the strength of a scatter plot, you need to use the Pearson's correlation coefficient, also known as the R value. So the R value is just a measure of the strength of a linear relationship. So how associated are the values or the explanatory variable with the response variable? So it's a measure of the strength of the relationship. So a higher, so R values will range from between -1 to +1, and depending on how close it is to the extreme, so -1 or +1, that will determine how strong your distribution is. Or sorry, not how strong your distribution is, how strong your correlation is, or your association is between the two variables. Again, for your R value, you will not be determining that by hand. You will be using your calculator to do this for you. Okay, so here is just a guideline of how you may describe the association. So you might say that there is a strong, moderate, or weak association. And then in terms of the direction, you might say that there is a strong, positive or a negative, or a no association in some cases. So if the R value is between positive 0.75 and 0.99, it's actually a strong positive relationship. Positive because we have positive values, and strong because this is a really high R value. If the R value is between 0.5 and 0.74, it would be a moderate positive relationship. If it's 0.25 and 0.49, it would be a weak positive relationship. And if it's between -0.24 and +0.24, there would actually be no association or reportable association between the two variables. Similarly, if it's between -0.25 and -0.49, we would consider that a weak negative relationship. And if it's between -0.5 and -0.74, that would be a moderate negative relationship. And if it's between -0.5, -0.75 and -0.99, that would be a strong negative relationship. Excuse me. So therefore, overall, the closer it gets to the negatives, the extremes, so the 1 and the -1, the stronger the relationship, regardless of what direction it is. And if the closer it gets to 0, the more weaker the association gets, until it becomes no association. Okay. And again, we can only use our values for linear data sets, which we'll come back to in a second. So just a quick example. Are these two distributions positive or negative? So positive usually just means that the values of the or the response variable values are increasing as we go from left to right. So in this case, that's actually the case. The y values are increasing as we go from left to right. So therefore, it would be a positive association. Whereas if the values start to decrease as we go from left to right, that would actually be a negative relationship. So very straightforward, just looking at whether the values are increasing or decreasing as we go from left to right. Okay, linear, nonlinear, or no association. So linear data will usually follow a particular trend, and that trend is going to be a straight line. But if it does not follow that trend, so for example, instead of the values looking at like a straight line, they might sort of follow a parabolic pattern, or they might be, an exponential function, for example, so something like this, or like this. That would be nonlinear. So not forming a straight line pattern. And then if the values just appear to be randomly scattered all throughout the scatter plot, then it's actually no association. So the explanatory variable does not affect the response variable at all. Okay, so just a few interpretation sort of statements. So we've already sort of looked at this, but if you have a question, you should have a structure in your data book already prepared to talk about how you might interpret an R value. So if your R value is linear, positive and strong, so a really high R value, The way that you're going to describe the association is you're going to say, it can be concluded that the y variable should increase as the x variable increases. So that's only when you have a linear, positive, and strong relationship. So here is just other sort of interpretations that you can just put in your summary book and use them when you're answering questions. So pretty straightforward here. Okay, so now we're going to be actually looking at the difference between correlation and causation. So whenever we're doing a study, which is what we're using data for, so we collect data in order to establish some form of relationship between two different variables, we're often looking at the correlation between those two variables. So correlation is essentially looking at whether there's some form of association between two variables. And then from correlation, we might establish some form of causation. So causation is when there is a meaningful association between the two variables. Something like cause and effect. So for example, it could be, ice cream sales throughout the year. So ice cream sales could be affected by a lot of different variables, but temperature might be one of the variables that might cause the ice cream sales to increase in the summer and then decrease in the winter. Whereas correlation, we're just looking at, what's the correlation or how are these variables associated with each other. So we're not establishing any sense of causation. And there could be various variables that could impact the correlation and the other than causation. So when we're looking at correlation, so for example, ice cream sales in the summer, it could be impacted by a lot of different variables. It could be impacted by temperature. It could be affected by location. It could be impacted by the duration of the summer, stuff like that. All of them are going to impact the ice cream sales. So there could be multiple confounders or confounding variables that are, affecting the causation between the expansion and the response variable, which are not really clear to us and we're not really accounting for. So here is just a little bit of a summary of bivariate data analysis, looking at the different ways of representing bivariate data in terms of the types of variables, looking at how to interpret the Pearson's correlation coefficient in terms of interpreting the shape or the direction, strength, and linear or non-linear linearity of a particular scatter plot, and also looking at the concepts of causation and correlation. Just a quick example here. So the relationship between resting pulse rate per minute in age group and age group is best displayed using. So first of all, we have a resting pulse rate in beats per minute. So first of all, what type of variable is this? So we have a numerical variable because we're measuring a quantity, and because the beats per minute is something that we're measuring, not counting, it would be continuous. And then age group. So age would usually be a variable that is, numerical. But in this case, since we're recording the age group, it's actually going to be a categorical variable. Because we're not really recording any measurements particularly. So, and then in terms of what type of categorical variable it is, we have an associated order. So 15 to 20-year-olds are younger than 21 to 30-year-olds, which are younger than 31 to 50-year-olds, which are younger than over 50-year-olds. So particular order, so categorical ordinal. So therefore, we have we have a numerical and a categorical variable. So a histogram, so if we look back to the different ways that we can represent data, so it's definitely not going to be scatter plots. And it's also not going to be back-to-back stem and leaf plots, because for stem and leaf plots, we usually have more than one categorical variable, which we do in this sort of case. But so it's definitely not going to be a time series plot, and it's also not going to be so it technically can be a parallel box plot. But would that be the best way of representing this? Probably not. So let's just look at the other examples. Histogram, again, wouldn't be the best way of representing this, because histogram is usually when we have, histogram is again usually to represent a univariate data. So no. So it's either parallel box plots or stem and leaf plots. So the actual answer is actually here going to be parallel box plots. So parallel box plots are the best way of representing this because we can have, for parallel box plots, multiple categories. For back-to-back stem and leaf plot, it's only 2 categories that we can compare at the one time. So if it was just, 15 to 20-year-olds and 21 to 30-year-olds, that would have been perfect to use a back-to-back stem and leaf plot. But if we have multiple categories, then we need to use parallel box plots. So, why do we need to use bivariate data? Well, or specifically scatter plots, is because they're really good at establishing a model. So model is essentially when we're using mathematical equations to predict certain things. So let's just say we have a distribution of, again, I'm going to use the orange example. Let's say we have a distribution of the weights of oranges and the height and the diameter of the oranges. And we plot that using a scatter plot. So let's just say we were to go out and we were trying to determine, so we establish, so we draw a scatter plot and then we use those points to construct a model. So now what that model will help us to do is predict certain points. Let's say we have a orange weighing, 500 grams, and we want to determine what the diameter is just by looking at just by knowing the weight. We can use the mathematical model to work out that diameter. Again, this is a pretty straightforward example, like why can't you just measure it? But imagine for something that's a lot more larger scale. In that case, it might be really hard to sort of, measure certain stuff. So in that case, a model will be really helpful. So the model is essentially just the least squares line of best fit. So essentially when we have a scatter plot and we draw a line of best fit. So for example, if we have this scatter plot and we draw a line going through this scatter plot, it's just the line that's essentially minimizing the residuals, which we'll have a look at in a second. But essentially it's a line that's going through the middle of these values, which you'll never be asked to draw from raw data. You will have to probably use some form of equation to do that. So you'll never be asked to draw a line of best fit just from looking at a particular data value. So what we need to do is once we have our data plot, we need to use some form of linear regression, which can be found in your calculator. And once you've done that, we can draw we can calculate a linear equation, which is essentially your mathematical model. Okay, so here is how we can calculate or how we can determine the least squares regression line. And the least squares regression line has this form. So it's y plus a plus bx, where the a value represents the y-intercept and the b value represents the slope. We'll have a look at how we interpret those values, but this is just the general form of a least squares regression line. So we will need to find what a and b is in every scenario in order to determine the model. So usually what will happen is in questions, you'll be given raw data. So you'll be given x variables and you'll be given y variables. And from there, you can put that data onto your calculator and your calculator will spit out these a and b values. Alternatively, you might be given certain descriptive statistics. So you might be told what the standard deviation of the y variable is, what the standard deviation of the x variable is, what the mean is of the y variable, what the mean is of the x variables, what the r value is. If you're given all the statistics, you can actually manually calculate the a and b values just by using these formulas, which are also in your formula sheet. So b is equal to r, which is a Pearson's correlation coefficient, which will be given to you, multiplied by the standard deviation of y, divided by the standard deviation of x. And then once you've found b, you can then go ahead and determine a by using this formula over here. And then from there, we can determine the a and b value we can substitute into the formula. Just one thing about the least squares regression line, it's not going to be written as y and x. You will have to actually write what those variables are. So if it's, for example, the weight and the height of oranges, instead of writing y equals a plus bx, you would say the weight of oranges, or whatever the explanatory variable is equal to a, whatever that is, plus b, multiplied by the explanatory variable. So the explanatory variable might be the height of the oranges, for example. So once we've done that, we have our model ready to go, and now we can use that model to make predictions. So we can actually interpret the regression line, and VCA will get you to do this. So they will, ask you to interpret what the y-intercept is and what the slope is. So the y-intercept is essentially what the response variable is going to be. So what the response variable is going to be if the explanatory variable is 0. So let's just say, so in this particular example, it's not going to make much sense. But if the weight of the orange was, 0 kilograms, what's going to be the height? Obviously, you'll expect 0, but in terms of the model, it might be a little bit higher or it might be a little bit lower. Just because it's a model, it doesn't 100% accurately represent real life. Okay, so that's how we can interpret the y-intercept. In terms of interpreting the slope, again, the way that you can interpret it is how much is the response variable increasing or decreasing for every 1 unit increase of the explanatory variable. So this will be really useful for determining if the if the y variables are increasing or decreasing over time. So VCA will be really, so again, having a really good structure when you're describing the slope or the y-intercept is really important in this case, because otherwise you'll get confused in the actual exam and you wouldn't know what to write. So again, having a really substantial or really sort of model structure of how to sort of phrase your response will be really important. Okay, so now we'll move on to the coefficient of determination. So the coefficient of determination is literally just r squared. So whatever the Pearson's correlation coefficient was, is just going to be that squared. And because the r value is being squared, the r squared value is always going to be positive, but it's always going to be between 0 and positive 1. It's not going to be greater than that. And the coefficient of determination gives us an information about the correlation of the two variables. How correlated are they? And the way that we can interpret the correlation of coefficient is that the correlation of coefficient tells us that r squared times 100%. So you convert whatever the r squared value is into a percentage of the variation in the response variable is explained by the variation in the explanatory variable. So you would have to substitute in what the response and explanatory variables are in your particular scenario. But this is essentially the overall structure, which you guys should be really familiar with. Okay, so now let's move on to linear regression. So how do we actually use a model, and then how do we assess whether the predictions we're making are valid and reliable? Well, if we are predicting a value within the data range, that is termed interpolation. And those values are actually going to be fairly reliable. So let's just say in a particular data set, you're given values between, let's say 10 and 30. So you're given a range of values, x values between 10 and 30. And let's just say you want to predict what the y value will be using your model when the x variable is 26. So in this case, as the variable is between 10 and 30, this is actually going to be termed interpolation, where we're essentially predicting a value within the data range. However, if the x variable is greater, so let's say we're trying to predict what the y variable is going to be when it's 45, when x equals 45, we can still interpret what the value is going to be, or we can actually still determine what the value is going to be. But when it comes to whether the prediction we made is reliable or not, it's actually going to be very unreliable, because we don't know if the pattern is going to continue after the 30-year mark. So we know from between 20 years, from 10 to 30, the pattern is like this. But soon enough, it might go like this. So we can't predict. So therefore, when we're predicting outside the data range, we call that extrapolation. Okay, just a few things. When we have predicted a certain value, we will have something called residuals. So residual is just the vertical distance between the actual data point, so whatever the actual data point was in the original data set, and the value we get when we predict it using the least squares regression line. So it's just this distance over here, for example. So once we've determined that distance, that's essentially the residual there. And essentially what the residual tells you is how different the value is from the predicted value, or how far away the actual value is from the predicted value. And it only works best if there are no outliers, because if there are outliers, that outlier might be over here, but it's an outlier, that's why it's going to disrupt the value. Okay, and then once you have all your residuals for all the different data points, all the different x values, you can sketch a residual plot. The residual plot will look something along these lines. So if there is a clear pattern in how the residual values are placed, we can actually say that the distribution is nonlinear. So this is how we determine if something is nonlinear or linear. And that is by determining whether the residual plot has a clear pattern or something like this, just a random scatter. So random scatter will mean that the residuals are close to the x-axis and that there is no inherent pattern. If there turns out to be a pattern, we might look at the original graph and try to determine what the distribution might be. Is it sort of like curved like this? Is it curved like this? Is it curved like this? Or is it curved like this? So once we have determined which one of these a graph looks like, and this is called a circle of transformations, which all of you should have in your data book. So once we've determined what the graph looks like, we can determine which transformation to use. And just a disclaimer, in the exam, you'll never be required to actually determine out of these three which one's the best. They'll usually tell you, log x is the best, so therefore use this to determine this. So you will never have to do this. But if your SAC's already passed, but if you did have to do it by hand, what you would need to do is you need to apply all of these transformations to the data. If your data looks like this, and then determine which one gives you the highest R value, or the highest R squared value. Probably R squared because it's 0 to 1, so there's no direction. So the one that gives you the highest R squared is the one that you should use. So let's say y squared gives me the highest R squared value out of the other two. So therefore I should use that as my transformation. So I hope that makes sense. Okay, so why do we need to apply transformations? Well, if we want to predict data using a model, we need to convert that data into some form of something that might reflect the transformation or might reflect the data. So for example, here, the data is like this. If we use a linear regression line, that might just go like this. So this value will be so different to the actual value, which might be over here. So therefore, to minimize this sort of error, we will construct a normal model, which might reshape features of the graph. Okay, so now we'll move on to time series. So time series are the same as a regular scatter plot, except there is only one explanatory variable, and that is time. And the response variable is usually whatever we're measuring. So for example, in this case, it's the sea level rise. And what the time series is really good for is estimating the trend of a certain value over a long period of time. So in this graph, we can easily see that the sea level is rising over time, which could be, of concern. So again, these types of graphs are really good for representing the relationship over time between two variables. Those two variables being time and also any other type of variable that you're measuring. So when we're describing trends in this time series plot, and it's called a time series plot because it's representing a distribution of values over time, we can have two different types of trends. So we can have an increasing trend where the value is a positive slope, or we can have a decreasing trend where the value is a negative slope. So in this case, we have a positive distribution. A positive or an increasing trend. Another thing that we can have is seasonality. So seasonality is essentially where we have regular intervals that are associated with particular seasons, months of a calendar, weeks, stuff like that. And these are usually to represent sort of something that has seasonal variation. So a good example might be something like, again, the ice cream sales. There might be much more ice cream sales in summer as opposed to winter. So therefore, this is an example of seasonality because it should repeat itself every single year. This is different to a cycle because a cycle, although it does have, the ups and downs, this sort of variation is, across a variety of different years. So although there are peaks and troughs, they're not going to occur within the same year. They're going to, occur through a plethora of years. So across a range of years. So as you can see in this graph, we have this sort of a peak, but that peak is going to reach, approximately 10 years to reach that peak, and then 10 years to come back down to normal level. So therefore, we have no therefore this is called a cycle. There can actually be seasonality within a cycle, but that gets really complicated. So VK usually don't like to put those types of questions. And lucky last, we have, not lucky last, but we also have irregular fluctuations. So irregular fluctuations is just the normal variations or small fluctuations in data, just as a result of the nature of data and how data sort of behaves. So basically, it's just a sort of like a cycle, but we have like a variety of different, peaks and troughs as a result of that. So, and these are inconsistencies in the data. So, so whilst we might represent a seasonality graph to look something like this, it might look something like this. Although we have that seasonality pattern, we can see these sort of like fluctuations, which is what the irregular fluctuation is. Okay, so now we'll look at structural changes. So structural changes are sort of just like rapid changes in the data, which divert the data from its normal patterns, such as shown here. So we have the data sort of consistent, and then there's a sudden change which drops the value by so much. And there could be a variety of different reasons which might contribute to this. But essentially just a sudden change in the established pattern. Excuse me again. And lucky last, we have outliers. So outliers are the individual data points that stand out from the general body of data. And they are essentially just really obvious on the data set or the graph. For example here, values are just divert from the overall pattern, essentially. Okay, so now we have, now we'll look at smoothing methods. So smoothing methods are essentially where you're trying to either remove irregular fluctuations or you're trying to remove, most of the time you're trying to remove the effects of irregular fluctuations, essentially just to smooth the data to make sure we have a better idea of the trends in the data. So there's two methods, numerical or graphical. So first we'll look at moving mean smoothing. So moving mean smoothing is to dilute the effect of large fluctuations. So basically what it does is it takes into account the surrounding data of each point to give a clearer trend flow. So an example of this is using this table over here. So let's just say we're trying to calculate the smooth mean value of time 2. And let's just say 3 moving mean. So we need to calculate the mean of these 3 values, with 13 being the center point of these 3 means. So therefore, essentially, we just add all 3 values and we get a smoothed y value. That is basic moving mean smoothing. And then we might do the same for 3. For 3, we might do 13, 6, and 14. So the values surrounding that 3. And again, we will get 11. And then 4, we might do that again. Now this will be 6, 14, and 6.5. So I hope that makes sense. So essentially what we're doing is we're averaging all the values. So for example, we're averaging the value 4, but we're considering the two values surrounding it because it's a 3 moving mean. If it was a 5, then we would consider 5 values or 2 values either side of the value that you're calculating. But what about if it's an even number that you're trying to calculate the moving mean for? For example, let's just say we're trying to calculate the moving mean of 3 here, but it's 4 moving mean. But we have 2 values on one side and 1 value on the other side if we want 4. So this represents a problem because essentially we can't really have an even sort of distribution, because if we do these 4 values, the mean of the x value is going to be somewhere around here. If we do these 4 values, it's going to be around here. But we want it at exactly one data point or at another data point. So essentially what we will do is we will calculate the mean of the first 4 values. So 2 values on one side and 1 on the other side. We will get a 10. And then the mean of the next 4 values. So 2 on now the top side and 1 on the bottom side. And then we will get the true means of those 2 sides. And then what we will do is now we will need to center that data. So centering just means we calculate the average of these 2 values now. And that will give us the smoothed y value. So this process is a lot more tedious as opposed to just doing normal moving mean, but something that does definitely come on the exam. Ooh. Okay, so now we'll look at moving median smoothing. So moving median smoothing is essentially where you have a graph and you're trying to calculate the medians of the graphs. So do I have an example? I'll just use a graph. For example, here. So if we were trying to calculate the median, the 3 median of this value over here, what we might do is calculate the median of the 3 values surrounding it. So therefore the median is over here. And then we might do the same for, this value over here. Where's the median? We have 1 median on this side, 1 median on this side. Oh, sorry, not median. 1 value on this side, 1 value on this side. And then this is the median. So on and so forth. We will need to do this for the entire data set. But making sure that we're only doing 3 at a time. So that's essentially the moving median smoothing, where we're using the graph to do a moving median. Okay, so now we'll quickly look at seasonal indices just in the interest of time. Otherwise, we would have gone through an example for moving median smoothing. But for seasonal indices, essentially what we're just doing is we're diluting the effect of any seasonal variation. So let's just say in winter we get a lot more ice cream sales as opposed to summer. But we want to determine, in 2020, did we do better or worse? Which is going to be really hard to tell most of the time. So in that case, we might use seasonal indices, which dilute the effect of the seasonal variation. And as a result of that, we get a really sort of straight graph, which you can model a relationship for. So how do you determine the seasonal indices? Well, there's a pretty straightforward formula. What we need to do is we need to add all the values in a data set for the particular year or whatever the seasonal period is, and then average it, and then average the data. So if it's, for example, summer, winter, autumn, spring, we need to take we need to add all those values together, and then we need to calculate the median, the average of those. And that will be the seasonal index of all the different values. We calculate all the average, and then the seasonal index is the value for that season. So whatever the value is, so value for season, and then we divide that with the total, with the seasonal average. So value of season, and this way we can determine how above or below that particular value is from the seasonal average. So value of season over the average, yearly average. Oops. Yeah. Cool. So season can again mean various things depending on the context. but usually it could be months, quarters, or weather seasons. So in terms of interpreting a seasonal index, there are a couple of ways that we can interpret it. So if the seasonal index is above 1, the way that we can term it is, let's just say it's 0.3 above 1, we can times that by 100 and we can say that it's 30% above the seasonal average, or that figure is 30% above the seasonal average. Similarly, if it's below, all we need to do is do 1 minus 0.87, or whatever that value is, minus, times by 100, again to determine the percentage. So we can say if the seasonal index is 0.87 during the winter, this tells us that the figures are 13% below average. So that's how we interpret seasonal indices. And now in terms of correcting for seasonality, we have a formula, and the formula is 100. So correcting for seasonality is essentially where we have a particular value, but we want to correct it. So what if there were no seasonal variation? What would that value be? That's essentially correcting for seasonality. And the way that you can do it is 100 over seasonal index minus 100. And that will give you your, so that will give you your, the value that you need to adjust the value by, or how to correct the seasonality. So let's just say we do this formula and we get something like 20 or positive 20. What that would mean is that the value needs to be increased by 20%. So it's not the same as interpreting the seasonal index. It's going to be a little bit different. So for example, if we had one seasonal index of 0.8, is not simply as decreasing by 20%. We do 1 over 0.8 minus 100. So what will that give us? So if we do it quickly on our CAS, I'm just going to quickly do it on my CAS. 1.25. We will get 1.25 minus 100. Sorry, not minus. Why do I keep on doing minus? It's 100 times by 100. Sorry. Oh, sorry. I used the wrong value. My bad. So it's going to be 100 over 0.8. Not 1 over 0.8. It's 100 over 0.8 minus 100. Which is 125 minus 100, which is 25. So we'll get positive 25. So what that would mean is that we need to increase by 25% in order to correct for the effects of seasonality. Okay, so now we'll quickly look at deseasonalization. So deseasonalization is essentially where you are so you have a value and you're trying to remove the effects of seasonalization in order to basically construct a model. Again, that's the purpose of seasonal indices. We're trying to remove the effects of seasonalization in order to construct a model. So deseasonalization, essentially what it means, deseasonalizing a particular value. And there is actually a formula in your summary book for this, which you will be using all the time. So the deseasonalized value is equal to the actual figure over the seasonal index. So let's just go through. So once you've deseasonalized value, you will get a set of deseasonalized values. And then from there, you can actually construct a model, which is called forecasting in this case. So first step, calculate seasonal indices for all the different seasons, which in an exam scenario will usually be given to you. Next step, calculate the deseasonalized values for each of the seasons or each of the months or weeks or whatever. Next step is to fit a linear regression line. So basically what we've looked at before, constructing a line. And for time, it can become a little bit complicated. But for time, let's say if it's like 2001, 2002, 2002, you can sort of have a sort of key. And you can say time equals 1 for 2008, for example, if that's your starting point. So just make it easier on yourself. And then making predictions by substituting in values for time to get a deseasonalized prediction. So then what you need to do is once you've modeled the value, you can make predictions. So you can use that model to, make a prediction about a certain value. Let's just say 20 years down the line, what's going to be the ice cream sales if we continue on this pattern. Again, it's going to be extrapolation, so the value is going to be very inaccurate. And then finally, we need to reseasonalize this prediction to get the actual prediction, because we've only calculated the deseasonalized value, not the actual value. Okay, so now we're going to actually skip this example. So you can have a look at this after lesson. The slides will be in the resources section. We will do this quick example and then we'll move on to the financial section. So for the financial section, before we move on to the financial section, we'll just look at this particular question. So here we're asked to determine what the pattern is. So what we can see here is we have sort of like a pattern where we're going up and down and up, relatively up and then down, and then up and then down, and then up and down and up and down every single year. So that immediately sort of looks like a seasonality sort of pattern. And if we look at the values going like this, it sort of looks like a decreasing trend, but it's not really that obvious. So I wouldn't really say it's a decreasing trend, although it does really look like a decreasing trend. So the answer here is actually going to be C. So it's seasonality with irregular fluctuations. Remember, irregular fluctuations are in every particular graph that you draw. So they will be found in every single sort of time series plot. Okay, so that was essentially it for the financial section. The data section. Now we'll move on to the financial section. So financial section has two components. We'll be looking at recursion and also financial modeling. So just some, tips from the get-go is getting yourself familiar with the finance solver. Your finance solver is literally everything. If you can't use this on the exam or you don't know how to use it, you can't answer most of the questions. Or you will, but they're going to be really hard to answer. And most of the time, some questions you just can't. So make sure when you're using the finance solver, you're really familiar with what negative and positive means and when we need to use it. Obviously, there'll be models. So you will have, annuities, so for annuities, the principal value will always be negative or stuff like that, or positive, stuff like that. Really being familiar with because sometimes you might be given models where you won't be told if it's an annuity, a perpetuity, a loan, or investment. And in that case, you'll really have to determine what the positive and negative is. And you can only do that if you're reading the scenario and you know what's happening. So negative is if the money is going to the bank and away from you. And positive if the money is going away from you, or you're giving money, so it's going away from you, but it's going away. Positive is if the bank is giving you money and it's coming to you. So always look at it with reference to yourself. If it's going away from you, negative. If it's coming to you, positive. So here is what the finance solver might look like. If you haven't seen this before, which I doubt, you will have N. So N represents the number of periods essentially. So if you're looking at a 2-year investment and it's compounding monthly, then it would just be 2 times 12. So that's essentially how many periods the interest is compounded overall throughout the term of the loan. The interest would therefore be, what the annual interest rate is. The PV is the principal value. So if it's a loan, how much you've borrowed from the bank. Investment, how much you've given to the bank. Or what you're starting off with, essentially. Payment, if you're making any additional payments. So for example, in a loan, you might be making payments to pay off that loan. So that will be the payment. Or if it's an investment, again, you will be making payments. Or you might not be making payments. You might be getting payments. If it's, for example, an annuity. And then the future value is how much money do you have, essentially, after, whatever the time period is. So after 2 years, for example. And then the PPY and the CPY are essentially just the number of compounding periods in a year. So how many times is the interest compounded, which is CPY, and how many times the principal is compounded in a year. which are usually going to be always be the same. So, okay, so now we'll quickly look at what recurrence relationships are. So recurrence relationships are essentially just financial or just any type of relationship that helps us to generate terms of a sequence or terms of a particular pattern using either initial conditions, so what we're starting off with, or the previous value, depending on what sort of relationship it is. Okay, so just as an example, we'll do a simple question. So the following recurrence relation can generate a sequence of numbers. So we have L0 equals 37, Ln plus 1 is equal to Ln plus C. So this is our actual rule, and this is our initial condition. So you'll all be familiar with these sort of units, so I won't be going through them in a lot of detail. But the value of, so we have been given that the value of L2 is 25, and we want to determine the value of C. So we know what L2 is, so if we want to determine what C is, in this question it's a little bit difficult, so we might need to go backwards. So we know what L2 is. So L2 is equal to L1 plus C. But do we know what, so we know what L2 is, it's 25. Is equal to L1, so we don't know what L1 is, but that is equal to L1 plus C. And what else do we know? Well, we know that L1 is equal to L0, or the previous value, plus C. So therefore, what we are trying to determine here is what L1 will be. So what we can do is we can rearrange for L1. So L1 is equal to 25 minus C, essentially. So we move C to the other side. So just using basic algebra here. And then in terms of L1, we know what L0 is. It's just 37 plus C. So then what we might want to do is we might want to let them equal to each other. So we might do 25 plus C, because L1 is equal to L1. So we might do 25 minus C equal to 37 plus C. And then moving on, sorry, my working out so messy, but then we can move this C to the other side. So we will get 2C is equal to, and then we can move the 37 to the left-hand side. So 25 minus 37, that would be negative 12. So therefore 2C is equal to negative 12, so therefore C is equal to negative 6. Alternatively, this could have been easily solved on your calculator using the solve function. So therefore the answer here is negative 6. A less conventional question, but definitely something that you are likely to get on the exam. Okay, so this is, again, so we've looked at what recurrence relationships are, but recurrence relationships can essentially represent two different types of sequences. So they can either be used to represent arithmetic sequences, or they can be used to represent geometric sequences. So arithmetic sequences are basically when we have a sequence where the values are being added by the same amount each time. So basically what's happening is we have a addition or subtraction of a certain number to get to the next number. And this is what the recurrence relationship will look like, essentially. So we have an initial condition, and remember, recurrence relationships represent or allow you to find a particular value given the initial condition and a certain value in between. Next, when we look at the nth term rule or the nth term relationship, essentially when we're looking at the nth term relationship, we can determine a particular value regardless of what we're trying to determine. And when that might be useful is, for example, a recurrence relation, we can only determine if we know what the immediate value before it is equal to. But for the nth term relation, we can determine, the 20th value in a sequence from just knowing the initial value, essentially. And these are the two separate equations that we can use. So essentially, we can have this recurrence relation, which is Vn plus 1 is equal to Vn plus d, where d is the common difference, or the value basically, or the number that you're adding or subtracting each time. And here we have this equation where we have Vn is equal to V0 plus dn, where V0 is essentially the initial value, and then d is the common difference, and n is the value that you're trying to determine. So if you're trying to determine the first value, the 20th value, the 50th value, for example, you just sub in what n is, and that will give you what your value is. So, for example, if we were to ask to determine u4, and this was our equation here, so u0 is equal to 2, that's our initial condition. Un plus 1 is equal to un plus 4 is our recurrence relation. So our common difference here is 4. So if we were to determine u4, we would first need to determine u1, then u2, then u3, then u4, using the recurrence relation, where we're using the value that we get for u1 to determine u2, then the value that we get for u2 to determine u3. That's different for the nth term relation because in this case, we can actually just use the previous term to determine, the initial value to determine u4. So straight away, we can substitute what n is to get 18 straight away. So we don't need to determine u1, then u2, u3, and then u4, and so on and so forth. So depending on what sort of question you're doing, the nth term relationship might be more useful than the recurrence relation. But often VCA will tell you what they want you to use. Okay, so now we'll look at geometric sequences. So geometric sequences are essentially where we are multiplying or dividing consecutive terms by a certain number. So for a recurrence relation, the rule will look something like this. Again, we'll have an initial value, but we can determine a particular value by using the previous value and multiplying by r. Whereas for the nth term relationship, we can determine a particular value by using the initial condition, multiplying by whatever the common ratio is to the power of what you're trying to determine. So I determine the 5th value, the 6th value, the 7th value, or so on and so forth. So again, here is an example. So if we're trying to determine u4, the initial condition is 2, and un plus 1 is equal to 2 times u0. So here, the common ratio is actually 2. So you're multiplying the previous value by 2 to get to the next value. So here, if you're trying to determine u4 using the recurrence relation, you will have to determine u1, then u2, then u3, then u4. Whereas if you're trying to use the nth term relation, you can just substitute it into the formula. 2 to the power of 4, you will get the answer straight away. So really convenient. Okay, so now we'll look at financial recurrence. So when we're looking at financial recurrence, there can be two particular scenarios. We can either have depreciation, which is a negative scenario where the values are decreasing over time. Or we can have a simple interest scenario where the values are increasing over time. Well, simple interest will actually depend on whether you have simple interest on a loan or whether it's an investment. But usually, if it's an investment, we will have simple interest, which means that the value is increasing by a certain amount every time. Okay. So now we'll go over the different types of depreciation. So depreciation is essentially where the value of something decreases over time. And for flat rate depreciation, it's going to decrease by a fixed amount in each depreciation period. And this is essentially therefore going to be an arithmetic sequence because it's decreasing by the same amount each period. So the formula that we will usually use for flat rate depreciation is very similar to simple interest. So we'll have, again, a V0 value, which is the initial value of the item. Usually it's going to be a car or a house, or for example, a printer, something that usually has value, a really large value. So let's say we have a car worth $20,000. And if it's decreasing by flat rate depreciation, and let's say that depreciation value is 5%. So it will decrease by 5% of the initial value each year. So what is 5% of 20,000? So if I were to quickly calculate this, that would be around $1,000. So therefore the value of the car is actually decreasing by $1,000 each year. So recurrence relation might look something like this. Vn plus 1 is equal to Vn minus 1,000. This is just an example. Now we'll look at unit value depreciation. So this is where instead of it decreasing by a flat rate every year, regardless of how much you've used it, for a unit value depreciation, it's going to decrease by depending on how much you've actually used the specific product. So let's just say you've used a printer for a lot more than someone else. Their printer might hold a lot more value as opposed to your printer because you've used it a lot more often. So unit value depreciation will depend on how much you've used the particular item. And there will usually be a unit value cost. So there will usually be a certain value. So for example, it might be, the printer depreciates value by 10 cents for every page that it prints. And then the formula is going to be exact same as the flat rate depreciation. However, now the values the D value actually represents how much it decreases every single time. And lastly, we have reducing balance depreciation. And in this case, for reducing balance depreciation, we have the value of depreciation decreasing according to a geometric sequence. So the older that something gets, the more it starts to depreciate, essentially. And this is the formula for how for the recurrence relation. Again, we're multiplying by the R value, where R is the depreciation rate. Okay, so now we'll look at more the financial side of things. So first of all, we will look at what interest rates are. So interest rates are essentially where if you have some form of investment or some form of loan, we are going to accumulate interest over time, or there will be a rate where the value of something might increase or decrease over time. So so we will have usually nominal interest rates. So let's say we have a loan and we have a 5% interest rate on that loan. And if it's compounding on a yearly basis, that will be the interest that we will either accumulate or get charged each year. But if it's accumulating on a more frequent basis, so for example on a monthly or a weekly basis, there's the interest that we're actually going to be charged overall in the year is actually going to be a little bit greater, just due to the nature of compound interest and the calculations involved. So that rate, the actual rate that we're actually going to be charged, is called the effective interest rate. So nominal is the one that is sort of like, this is what we're going to be charged. The effective interest rate is how much we're actually going to be charged if it's compounding on a more frequent basis. So there's actually a formula to calculate the effective interest rate from the nominal annual interest rate. So this formula is in your summary, your data book. But again, you don't need to use this because you have an interest conversion menu on your calculator. So again, so if we're using this formula, what R is just going to be the nominal interest rate. The N is going to be the number of compounding periods a year. So is it weekly? Is it monthly? Is it fortnightly? So on and so forth. And then R effective is just going to give us your effective interest rate. Okay, so now we're going to look at a few investment types just quickly. Obviously, we're not going through them in so much detail just due to the time limitations, but we'll just quickly go through what they actually mean and where they might be applicable. So annuity investments are essentially a type of investment where you have a large sum of money invested into an account, and you're depositing and you're withdrawing certain amount of money each time, just to give a scenario is, let's just say after you retire, you have a big sum of superannuation. You might invest that into an annuity investment, and then over time you're going to get payments from that annuity And that's essentially going to fund your life. So overall, annuities, you require a really large sum of money to invest, and the value of that annuity is going to decrease over time because you're taking money out of it. But it's also going to grow over time a little bit as well, because you're essentially getting interest from the bank. So the money is going to pay you interest for keeping money in their bank. And that's essentially, so let's say you started off with $50,000, the value is going to increase slightly, not too much, but since you're withdrawing a lot more, let's just say you're withdrawing $2,000 per month, the value overall is going to decrease over time. So that's essentially an annuity. This is different to a perpetuity because a perpetuity is essentially where the interest that you're getting in each payment period is the payment that you're withdrawing. So let's just say you have $100,000 invested and you're getting $500 of interest every month. And the $500 that you're getting in interest is what you're going to withdraw every month. So because you're withdrawing the same amount of money that you're actually getting in interest, the value of the perpetuity remains constant. So it's not going to grow at all over time. And it's going to remain relatively constant. Well, not relatively, it's going to remain constant. Because you're not allowing the perpetuity to grow and you're not allowing it to decrease either. And this is usually applicable to something called a scholarship fund, where a large sum of money, millions of dollars, are invested, and the interest that is generated each year is given as the form of a scholarship. This is really good because this means that you don't need to essentially, get new money to give to scholarship students. And what that means is you just require a really big sum of money invested initially, and then the students are going to benefit from it over, indefinitely. So that's the benefit of perpetuities. Again, it's a geometric relationship. So both annuity investments and perpetuities are actually geometric relationships because we're accumulating compound interest. However, the values are decreasing as well. So for perpetuities, it's staying constant, but the values for annuities are decreasing over time. Just quickly, before we move on to the last part of the section, we're going to look at amortization tables. So amortization tables are essentially a useful tool to illustrate basically any type of financial situation. So either it being a loan or it being an annuity investment, probably not a perpetuity, but yeah, so either of those two. And it's really good because it tells you your payment number, your payment amount, your interest paid, so how much of your payment is actually going towards interest, your principal reduction. So if it's a loan, how much of your, essentially what you're paying, how much of that is actually reducing the principal value. And then lastly, the balance of the loan. How much is your balance decreasing overall? This is just a really good visual tool to represent that, as opposed to doing, calculations every single time. There's a few formulas that might be useful when you're calculating what these specific values are. So principal reduction is essentially just the payment minus the interest. So what is the payment that you're paying? And then you subtract it from the interest that you're being charged. The interest paid is essentially just the interest rate multiplied by the previous balance. So whatever that interest rate is, 2%, 3%, 4%, whatever. And as you can see, the interest rate is actually decreasing over time because as the value of the balance of the loan decreases, more and more or less and less interest is generated. So therefore, if you have a really high principal, you're going to pay a lot more interest, and over time, it's going to decrease. And the balance of the loan is just going to be the previous balance minus the principal reduction. So principal reduction is essentially, as the name suggests, how much is the principal being reduced by in that particular payment period. Okay, so now we move on to, so we're going to skip this question and we're going to move on to the exam side of things. So the first and foremost tip that I like to give everyone is forget about your SACs. They're over now. A lot of the skills that you would have learned from the SACs probably won't transfer too much into the exam. Definitely the content will transfer, but the skills that were required for the SACs, especially the data SAC, I would say, are not required in the exam. So, and second of all, SACs are only worth 34% of your score. Exam is worth 66%. So if you're going to stress about your SAC marks and not focus on the exam, you're essentially doing yourself a disadvantage here. So go back over your SACs, that's what I would say. Look over your mistakes and try to improve. But don't be really just focused on this one question that you got wrong, because it might not be that important in the grand scheme of things. Okay, so organize a bound reference if you haven't already. A bound reference is, I would say, the first thing that you will try to organize now. So in these term 3 holidays, try to get your bound reference done as soon as possible. And when you're doing your practice exams, use the bound reference so that you get familiar with your bound reference and you know where everything is relative to each other. So when you get stuck on a question, you're not spending time looking through your summary book, finding where you might find help for that particular question. Instead, you're spending more time on actually doing that question. Thirdly, I'm actually going to say, when you start doing practice exams, work out what modules you'll be doing first. So on the, not 2 modules you choose, what I want to say is choose which modules you're going to do first. So the data that you're really strong with, you might start with data first, or is it, matrices that you're really familiar with, you might start with matrices, but work that out as soon as possible. Otherwise, if you're like me, just work through the exam chronologically. Just depends on what you're familiar with. Next, keep it simple and concise. Your summary book does not need to be, literally every single resource that you have accumulated throughout the year. Your textbook, your practice acts, your every single exam that you ever done, every single piece of notes that your teacher has given you. Keep it concise. So my one was really brief, really short, and I knew exactly where everything was. So here is just a few of the pages from my summary book that you can have a look at. So really concise, and that just makes it really easy to find what you're looking for straight away. Fourth of all, I would say, make sure you understand all the content. If there are things that you're unsure about, definitely ask your teacher or tutors, friends, or watch, some of the resources on the HR Notes website would be really helpful in, clearing any sort of doubts you may have, and also just really consolidating your knowledge. So if you don't want to start practice exams straight away, you might want to spend some time understanding the content. So doing a few, revision sort of things, just like going through the content, understanding, make sure you're understanding everything. But practice exams make perfect. So start doing practice exams as soon as you can, because they are really just going to improve your overall importance. For subjects like humanities, the value of practice exams actually decreases over time. So if you're doing, thousands of English exams, the value that you're going to get out of these exams is probably going to decrease over time. Whereas for further, it increases as you go along. Well, for most people, not always. It's not always going to increase, but yes, the more exposure that you have to the practice questions, the style of questions, the more familiar you're going to be with the further maths exam. Secondly, you need to aim to do about 8 practice exams minimum, at least the ones in the current study design. Not the current, but the one immediately before this one, which is going to be really similar. Try to do the exams from those study design at least. You don't have to worry about the ones that are before them. You can if you want to have extra practice, or you don't have any other exams to do. Company exams I probably wouldn't recommend, just personal advice. Some of the questions are either too easy or too difficult. I would just say weaker exams. So if you have run out of the current study design exams, do the ones from the old study design. But I personally just wouldn't do the company exams, like the NEET ones. Might do the NEET ones. They're actually pretty good, but I usually don't do any TSSM or like the other ones. And make your practice exams count. So don't just do millions of exams without checking them, without getting feedback on them. Really try to get really appropriate, really constructive feedback. Look through the exam reports. They're literally a golden resource when it comes to practice exams. So spend a lot of time looking through the exam reports, looking at what students have done well in, or what they haven't done well in the previous year, as well as the years before that, and then focusing on those sort of topics. And do the exams under timed conditions and exam conditions if you can. Obviously, the first few ones that you're going to do are probably not going to be 100% under timed conditions, but yeah, slowly you should start getting into that sort of rhythm of doing them under timed conditions. Okay. And choose carefully when you do them. So at the beginning, this might not really make sense, but as you get closer and closer to the exam, try to do them extremely under exam conditions. So what I mean is, do them at the exact time when the exam is scheduled. So like if it's in the morning, do them in the morning. If it's in the afternoon, do them in the afternoon. Really try to replicate those conditions as best as possible. If your teacher and if your school hosts any type of mock exams, I know a lot of schools do and a lot of schools don't. Those are really good to just go through, even if you don't, really find them useful, or you're not prepared, just to replicate those exam conditions. Understand the sort of stress that you might experience in the exam sort of room. Just really going to be helpful overall. Another thing that I would probably say is keep a track of your mistakes. So something like this is probably what I did, where I had the exam that I did, the mark that I got, when I did the exam, what sort of conditions I did that exam in, how many marks did I get for each of the sections, stuff like that. What that will do is it will allow you to show your progress over time and just really see if doing those practice exams is actually helping you, or are you just wasting your time. And lastly, I would just say make a exam plan. Making an exam plan would really be helpful in terms of structuring, when you should start doing your exams, when you should stop doing your exams, just overall how long you need to do all the exams that you aim to do. Make an exam plan for all your subjects. Spend, even if it takes you like one day to make that plan, that's way more effective than going into the exam period and being really super confused on what to do exactly and what exams you have done, what exams you haven't done, what you need to do to prepare for any particular exam. Just really being organized is what's key here. But lastly, make sure you look after yourself. So this exam period is probably going to be the most stressful period of year 12. So really try to get plenty of sleep, exercise, and eat well if you can. Not if you can, but try to do it as much as you can. And also make sure that if you're in year 11, really try to, what I was going to say is really try to make this a really, as opposed let me start again. If you're in year 11, just make sure that you treat this as like a year 12 subject. Like what I mean is if you are in year 11 doing a year 12 subject, just think of it as sort of like a subject that you're just like, gonna put in your bottom two. Really try and focus on this and really try to get the full experience, because it's really going to help you next year when you actually get into year 12. But if you're in year 12, you might already be exposed to the exam structure, so you would have done like the gap, for example, or you might have done year 11 subjects. So overall, just really trying to get familiar with the overall VCA sort of exam structure is really important here. And in terms of the actual exam, do the multiple choice question. All the multiple choice questions are worth 1 mark, but not all exams are as easy as each other. So the trend that I've noticed is as each of the questions progress in each of the sections, they get harder and harder and harder. So for example, question 1 of data will be super easy, and then question 16 of data or question 15 of data is going to be much more difficult. Same goes for the financial and the matrices section. So question 1 of the matrices will be relatively easy, and the question 8 will be relatively harder. And then try not to freak out. This is personally easier said than done. Definitely easier said than done. When you get into the exam room, that scenario, it just freaks you out naturally. So that's why I'm saying try and get into, or try and do the exam under those conditions, replicate those conditions as much as possible, so that you know how to, just basically you know how the exam sort of works, and you don't freak out when you actually get into the exam room. And another tip for exam 1 is when you're doing multiple choice questions, make sure you shade the correct bubble, and in the actual, make sure you circle it in your book, in your question book, and then you look at it, and then you circle it in your answer sheet. So make sure you don't just straight do it on your answer sheet, because if you're at the end trying to check if you've circled all the questions correct, it's easier to just like go through all the correct ones that you've circled on the exam book and just look if you've done them correctly. But that's basically it for my exam tips and just overall lecture. Thank you everyone for attending the lecture, and good luck for your exam. I hope you do the best that you can. Bye everyone.